Okay, so good afternoon, dear audience, dear students, dear scientists. I'm Aidas Matioshus from Laser Research Center. Maybe you see this building behind me. For today, it's my great pleasure to introduce you Professor Daniele Faccio from University of Glasgow. He is a Royal Academy Chair in Emerging Technologies and Fellow of Royal Society of Edinburgh and Optical Society of America. He joined University of Glasgow in 2017 as professor in quantum technologies. He now leads the group, Extreme Light Group, and at the same time, he's a director of research for the School of Physics and Astronomy. He is also a general professor of the University of Arizona and previously was professor at Herod-Watt University, Edinburgh, and assistant professor at University of Insubria, Como. And this is the place where I met him at the first time. He has already published over 130 scientific articles, and I forgot to say that he has a beautiful family, wife Sylvia and son Cesare. So greetings for them, Daniele. And I'd like to talk about awards, Daniele's awards. And in 2009, he was awarded by European Community Marie Curie Fellowship at ICFO, Barcelona. 2015 was he received prize, so Philip Leverhulme Prize in Physics. 2017 was the Royal Society of Edinburgh Senior Public Award. Nobel Prize of Sorin still not, but I think he will. Yes, I think about you and about Nobel Prize, I believe and I wish you. And now I would like to explain why I'm talking about Nobel Prize. Because the last invited laser session speaker of Open Readings was Professor Gérard Mourou, and it happened in 2019. And he was awarded a Nobel Prize in Physics in 2018. And it was a really interesting situation because he agreed for the lecture just before he received a Nobel Prize. And in 2020, the Open Readings was postponed because the COVID situation here in the world. And when the organizers asked me, organizers of this conference, Open Readings, asked me, could you recommend a good Frisian speaker for laser topics? So I immediately emailed you, Daniele, because 2 years ago in 2019, you presented amazing lecture on light and flight imaging here in Vilnius. And I would like to cite your words. We can see behind walls in the new future. We will probably be able to see directly inside the human body. This is just the beginning of new form of photography. And I'm sure that in the near future, there will be much, much more calm. So Daniele, you are welcome with your lecture, Imaging with Time, from Multipath Imaging and Healthcare Application. So Daniele, this is your 45 minutes of responsibility. Welcome, Daniele.
Okay, thank you. So let me share screen and just get the presentation up and running. Bear with me 2 seconds, sorry. Here we go. Okay, and you said you wanted a green laser, so let me just get that green Laser pointer. Okay, so thank you very much for that very kind introduction, Idas. Yeah, I'm honoured to be here to talk today, especially after your last speaker, Gerard Moreau. Although I very much doubt that I'm going to be able to follow his footsteps when it comes to the Nobel Prize. But I really thank you, and it really is an honour to be able to speak here today. I've got many friends in Vilnius. Idas is one of them, but I see other names also in the attendance list. So it's really a great pleasure to be here, and I have visited Vilnius University to work with you guys many times, and it's been a long time since I've been there, but hopefully the COVID situation will allow me to come back very soon. So let's get on with the actual talk. What I want to talk to you about today is indeed sort of an emerging technology, but it's rapidly establishing itself. Let me start by giving you an example of what we mean by this new form of photography. And what you're seeing here is a laser pulse, 500 picosecond green laser pulse, which is propagating in free space. And what we're able to do, as you can see with this form of photography, is we're able to take movies at about 1 trillion frames per second. There are people working now at tens of trillions of frames per second. So picosecond resolution allows you to freeze in time the motion of a laser pulse as it propagates in free space. And so what this talk will be about is this concept of imaging with time. So adding not just time in the sense of the standard sort of the movie sense, but time at sort of the picosecond level, where you can actually freeze the details of how light is propagating, how it's moving. And some of the recent things we've been looking at is this concept of multipath imaging, which, as I'll show you, is sort of a very encompassing sort of concept. It encloses many different examples. And what I want to try and do is just give a very brief overview of our sort of journey, starting from that first video that I showed you a minute ago, all the way to some applications, in particular in the area of sort of healthcare solutions. So the basic underlying technology, at least where we started from, but we're sort of moving beyond this at the moment, is based on, you can see here a basic model of what we call a SPAD camera. SPAD stands for single photon avalanche diode. So these basically are just diodes which are driven with a very strong reverse bias voltage. So when a photon hits the diode, it creates an electron hole pair, but because of the very strong reverse bias, this electron leads to a runaway avalanche effect, and it gets effectively multiplied, and therefore gives you, for just one single photon, gives you a very large voltage output at the output of your diode. And people have been using single pixel SPAD sensors for many years now, especially in quantum optics labs, for example. But the recent, when I say recent, it's several years now, but for the past 4 or 5 years, there's been a very strong development towards making actual cameras out of these devices, to the point that now you can find them even in some models of your phones, even if though you may not be aware of that. So that's just to say that this is a technology which is relatively well established in terms of how people make these things, that there's still a lot of work that can be done in understanding new ways how to use these cameras. So I want to very quickly, in the next slide, just give you a very quick overview of how these cameras, so the fact that you're detecting a single photon, how that can be used to gain this sort of picosecond temporal resolution that you can then associate to the images that you're recording. So the typical way of operating these cameras is with what is called active illumination. So you actually use a laser to illuminate the scene. I was showing you a video where we're showing a laser pulse, a pulse laser. The pulse is bouncing off mirrors. The pulses are propagating in free space, in air. So every now and again, there's sort of a low but finite probability of photons scattering towards the camera. The camera is triggered by a TTL signal from the laser, and that starts a stopwatch. So it gives you time zero. And when the photon hits the detector, because it's operating in Geiger mode, this is a photon, so sort of quantum mechanics effect, if you want, it gives off a single click, and you can use the difference in time. The electronics is sufficiently precise that it can measure the difference in times between the start coming from the laser and the click coming from the photon, to measure that time in picoseconds. So essentially what that gives you then is sort of 3D data cube where you have X and Y, the usual spatial information. And then on the, you have another axis where you actually now have the temporal evolution. And so what you do is you repeat this. So these detectors can only measure one photon at a time. So in order to build up an image, what you do is you use, for example, a high repetition rate laser. You repeat the measurement many, many times so you can build up a histogram of events that will give you the temporal evolution of the laser pulse. And then you can build these videos, such as the one that I'm showing you again here. I did also just want to I told you that I was going to sort of give you an overview of my journey, at least, in this research field. And for me, everything started actually with this video that was originally shown. The first time I saw it was in 2012. It was at a TED talk given by Ramesh Raskar from MIT Media Labs. And he was showing what he was calling slow art. So this artistic rendition, if you want, of a laser pulse propagating inside a Coca-Cola bottle. And it was performed back then, not with SPAD cameras, but with a street camera, so rather expensive and bulky, and took a very long time to take this video. But nevertheless, this is like, if you want, one of those wow moments that every now and again you have as a scientist when you see something for the first time and you say, wow, you know, I want to be able to do that as well. And so this is what got us thinking about, you know, are there other ways to do this? Is there a technology that can do this, which doesn't cost £200,000, but maybe costs £1,000, or maybe one day even sort of 100? I talk in pounds, but if you want US dollars, you know, could this cost maybe $100 US and be accessible to everyone? But most importantly, I guess the question is, you know, this is all very, very intriguing and artistic, if you want, and nice. But is there anything useful that we can do with this technology? And that's what the rest of this discussion will be about. So one of the first things we started looking at, and again, inspired by the same group at MIT Media Labs and led by Ramesh Raskar, was this idea of using this technology to see behind corners. So we can't directly see through a wall at the moment, but there are several groups around the world that are trying to use this very high temporal resolution for imaging around the corner. And the basic concept actually is quite simple. What you do is now you're shining your laser, you've got a hidden object that's hidden behind a corner with respect to where you are with the camera. The idea is that you send out a laser pulse. This will hit a floor, it will hit the ceiling, a wall, whatever. But it hits a surface, and then this will scatter into a spherical wave. This spherical wave of light will then propagate behind the corner. It will hit the hidden object, reflect back, and then it will rescatter again. Here I'm just imagining that the camera is looking on the floor, but usually we use a wall actually. But it scatters as this rescattered sphere of light passes through the field of view. It can be collected by the camera, and it can be used to provide a 3D localization of the hidden object. And if you have enough temporal resolution, it can actually be used for full 3-dimensional imaging of the hidden object. So I'm showing these spherical waves. I just wanted to give you an example of another video where you can actually directly see these spherical waves as they're being recorded on the camera. So it's a similar scene to before. This is the field of view. This is raw data, laser pulse passing through the field of view. And here you see these spherical waves of light. Essentially what is happening here is every time the laser pulse hits the mirror, there's always a little bit of dust or imperfections on the mirror that will scatter some of the light into a spherical wave. And then this wave is intersecting this black cardboards that you see in the background here. And then that's what we're collecting, these sort of banana shapes, or these spherical waves. It's an intersection between the spherical wave and the wall in the background. And you can use this information, you can use the shape of the spherical wave, so the direction in which it's propagating, for example, and the time at which you see it to very precisely locate the position of your hidden target. So the maths for locating a hidden object is actually extremely simple. You have the distance from the laser spot, which is this first term here in the equation, hits the object, and then from the object back to the pixel in your image is another distance. That's the second distance here. And that is equal to the speed of light times the time that it took for the light to go from the laser spot to the object and back again. And this is where you're using the temporal information from the camera. So this equation, distance 1 plus distance 2 equals a certain time times c, is just the generic equation of an ellipsoid. So I've drawn one here in this green circle, but I have many, and so this essentially this green circle gives me the locus, the position of all the possible places where the object could have been. But now I have many different pixels. On this camera, I had 1024 pixels. So I can repeat this calculation for 1024 different points. Each one will give me a slightly different rotated ellipsoid, but all of these ellipsoids must, of course, have in common one point, which is the location of the object. So what you can then do is take the 1024 probability distributions, if you want to, and just multiply them together. Where they don't overlap, you'll be multiplying some of them will be 0, so you'll get a 0. And only when they overlap do you get something different from 0. And so there's only one point where they all do not where they all do overlap. And that will give you, therefore, the location of the object. And this sort of maths reconstruction is so simple that we're able to show that, for example, you can do, this is data taken in real time. So you've got a clock here. We were taking data at 1 second, so 1 hertz intervals, and tracking in real time an object as we moved it behind this sort of dark stripe here shows where we had the wall. And so this is our first work on this back in 2016. Now, and since then, we progressed greatly. I mean, we over the next couple of years, we extended this. So if you look at the vertical scale here, this is the distance in centimeters from the camera. So we were only operating at about 1 meter distance from the camera, but now we can operate that up to about 100 meters away from the camera. And the paper was published just 2 weeks ago from a group in China where they were doing something similar, but now at the distance of more than, I think it's about 1.5 kilometers. So they're going from one skyscraper to another. And the place where the camera was held and the place where they're trying to image behind a corner was 1.5 kilometers away, which is quite striking. But what we've been looking at in a bit more detail is just how much information is encoded in this temporal dimension of the data. So what I'm showing you here is just one single pixel from the camera, and we're looking at a person who is hidden behind a corner several meters away, but dressed, exactly the same person, but dressed either with black trousers and a black shirt or black trousers and a white shirt. And you can see that the temporal signal, so the horizontal axis here is time in nanoseconds. The temporal signal is very different. And so that then sort of raised questions of how much information does this actually contain? You know, if I didn't know who the person was or who they're dressed, and all I was given was these histograms, temporal histograms, is it possible to maybe pull out the identity of the person or pull out where they're standing or what they're doing just from this temporal trace on its own? And I forgot to make a link of why in the title I was talking about multipath imaging. And this is indeed all about multipath imaging, because remember what you're doing is you're sending light onto a wall. That's the first path. Then the light is propagating behind the corner. That's the second path. Then it hits the object, propagates back, third path, and then it has to rescatter again. And with the fourth path, finally reach the detector. So in this sense, it's a multi-path, or if you want, it's a multi-bounce form of imaging. So how much information do you actually have have in this in these temporal traces. So the first thing we tried to do was just use machine learning and build an artificial neural network for non-line of sight imaging by essentially collecting lots of data from different people standing in different positions. So I named these positions with letters of the alphabet, A, B, C, D, and so on. And then we had 3 different people standing in all of these different positions whilst we were taking the data. So these are pictures of the 3 different people. And what I'm showing you here is what is called, in machine learning, is called a confusion matrix. Essentially what you do is on the vertical axis, we're plotting the ground truth. So this is position A, B, C, D. So we knew where the person was standing. And on the horizontal axis, I'm showing the prediction from the artificial neural network. So it's given just one single temporal trace from the multipath data. And it's being asked after the training session, it's being asked to identify where the position of the person was. And dark blue means 1, meaning that 100% of the time, so all of the time, it was correctly identifying the position of the person. But what I found really interesting is this smaller confusion matrix. We only had 3 people here, but you can, and more importantly, I should add, although in the photograph here, these people are dressed with different clothes, in this confusion matrix, the people were all dressed in exactly the same way. So here we can see that we're correctly classifying the actual identity of the person, and not based on how they're dressed, but actually on their body shape. So that's quite remarkable. It doesn't really demonstrate anything other than the fact that there is a lot of information in just that single temporal trace. And we'll be coming back to this concept in a moment. So in parallel, though, I mean, other people have been also looking, of course, at these sort of non-line of sight imaging technologies. I wanted just in 2 slides give a very brief overview of the various hardware approaches that have been used. And you can find more information in this review paper from last year. But essentially, people have used anything and everything from single pixel APDs, SPAD cameras, I've spoken about that, street cameras. This was the first sort of measurements that technology that people were using, to ICCD cameras, even CCD cameras, so not using temporal information at all. And in terms of the reconstruction software, I don't have time to go into detail about this. And I only showed you a very simple approach that allows you to detect the location of a person. But various research groups, in particular, Andreas Welten and Gordon Wettstein, have been working on more complex approaches that allow you to do full 3D imaging. And going back to the first measurements in 2012, these measurements were taken with a street camera with a relatively simple back propagation reconstruction technique. All combined took several hours of acquisition and computational effort to get this 3D image. 2 more recent versions of these approaches, the light cone or so-called FK migration techniques from Gordon, and the phaser field approach by Andreas Welten. I mean, now we're talking about building, look at the complexity of these 3D images. It's just amazing. Remember, so these are room-sized objects. This is an actual bookcase here with a statue. These are actual 3D rooms hidden behind a corner. And the whole data acquisition and processing is now taking the time of order of 1 second. And so just look at the progress over 5-6 years that this field has achieved. It's quite remarkable, very promising for the future. So I know this is being recorded, so I won't go through the details here, but here are some of our papers on this topic if you're interested in reading up a bit more. But I would encourage you to look at this, start from this review paper, where you'll find a lot of details and, of course, all the recent papers referenced. So moving forward and going back to this a moment, to this concept of imaging using only temporal information, and how far can we push this? What can we really do with this? So I want to very quickly just sort of go over the concepts of the standard paradigms for imaging. The trivial one, and I'm not saying anything surprising here, is the usual way in which you image is that you assume that you have, for example, a single illumination point. Here I'm showing a laser, but it could be the sun, for example, or the lights in your house. These illuminate the scene, the little dinosaur here, and then the light is reflected onto your camera. And the reason you see an image is because your camera has lots of pixels, and those are what give you the spatial resolution. Very obvious and very trivial. You can also do this the opposite way around. So you can have what is called single pixel imaging, or often sometimes referred to ghost imaging, depending on the protocol you're using. But essentially you're flipping the pixelation now. So your detector is a single pixel, so it has no spatial resolution. And instead what you're doing is you're pixelating, you're putting pixels on the illumination. So you're using a form of structured illumination if you want. And the easiest way of doing this, and the normal way, most people nowadays, the way they do this, is you shine a laser or a light source onto a DMD or some form of spatial light modulator, and you project patterns onto your object. And by projecting many, many, many different patterns and reading off here the total reflected intensity and combining that information, you can pull out an image. So there's a third approach to this, which people had not looked at in the past, and that is have no pixelation whatsoever. I have a single light source, my laser, no pixelation, no spatial structure, just flood illuminate the scene, and then collect the reflected light on your single pixel detector. But now what you're doing is you're recording very carefully the temporal information. So you're recording the echoes of light which are reflected from this object, and the shape of the object will give you a pattern of light which changes in time. And so the problem here though is, I mean, there's a very good reason why people don't why standard cameras do not work like this. One reason is that you need the very high temporal resolution and you need a pulsed laser. But the real reason is that the reconstruction of an image, of a 3D image or even a 2D image from temporal data alone that is collected from the whole scene is what is called a very ill-posed problem. In other words, you do not actually, if you look at the maths of the problem, you do not in reality have enough information in this sort of temporal trace on its own to pull out a full 3D image of the scene. And you can see why this is. So any intensity at a given time, if I try to back propagate the field that could have generated this signal at a certain time t, you can understand that this will give a bit like the ellipsoid I was showing you earlier on. From just one pixel, when I trace back, I will have a whole circle of points that are all equally distant from my detector and therefore will all arrive at the same time. So the only thing, if I have no other information of the scene, from a temporal trace alone, the only thing I can back propagate and reconstruct is a series of circles in the scene. So you need to find a way to introduce this missing information. And the way we did it was, again, using an artificial neural network or machine learning, where basically what you're doing is, this is essentially just statistics, if you want, and curve fitting. You are providing all the initial, the missing data through the training process, where you're feeding the algorithm many, many thousands of examples of various kinds of scenes combined together with the actual temporal traces that these scenes generate. And so you have in other words, you're building in a statistical prior into your reconstruction. But this is the final result. This is what we get. I'm showing in the left-hand column here, except the actual measured temporal traces from the scene. On the far right-hand side, you see the ground truth measured by what is called a commercial time of flight camera, where color encodes depth. So this is 3D imaging. So you see the 2D spatial profile and color gives you distance. And the middle column shows you what we are reconstructing with just from one single temporal histogram through that is passed through our pre-trained artificial neural network. And you can see, when you have one person with a background, it works quite well. Two people, it works quite well. Every now and again gets a bit confused, but by and large, it's correct. And then you have various objects here. You have a square, the letter T. When the T is quite close, it works okay. When it's far away, essentially you're losing temporal resolution, or it's becoming harder to map the temporal resolution onto a spatial image, and it starts to work less well. But in the meantime, since we published this work last year, we've moved forward a little bit and realized that actually this multipath problem is heavily affected by the fact that light is decaying very quickly after each bounce. When light scatters off a wall and it scatters into a spherical field, that field is decaying as 1/r squared. So every time, if you've got a 3 bounce problem, for example, you have a 1/r to the 6th decay in the signal. And this really limits what you can do. But if you turn to other technologies, for example, radar or sonar, so ultrasound, these actually reflect off walls very similar to a mirror, and the decay of the signal is less intense. And so what we've developed is this technology that we call Echosense, where we're using, again, still artificial neural networks, but for multipath 3, now it's true multipath 3-dimensional imaging, where we're using both radar and sonar, and actually showing that we can, this is sort of like a cartoon sketch of a scene where you've just got to like this cuboid thing and you want to reconstruct its position. But we're really using the full potential of multipath data all the way up to, several bounces from the scene. And what we've shown is that there's a huge amount of information contained in the multipath data that allows you to actually significantly improve upon what I was showing to you in the previous slide. So bear in mind, in the previous slide here, we had picosecond resolution. With the radar, you can only get of order of nanosecond resolution. Yet, because we have this multipath information, the images we're getting are a lot better. And one way of understanding this is that, so here I'm showing you a picture taken from the internet of Charlie Chaplin in a house of mirrors. And this kind of, remember what I was saying, the radar signal or the ultrasound signal bounces off a wall as if it were a mirror. And you can see here that the first bounce, so I send out my signal, and I just get the first bounce, is just going to give me a direct or something similar to a direct image of Charlie Chaplin. But the multi-bounce data, so the signals that have bounced multiple times between the object and the mirror. So for example, light here has bounced off Charlie Chaplin's back onto the mirror and then towards the observer. I can see his back. Or if I look over here, I can see the side of Charlie Chaplin. And if I were to put mirrors on the ceiling, I would also be able to see him from the top and from below. And actually, what we did was, the first thing we did was we just interested in the amount of information that's contained in this multipath data. And you can calculate that. You can use information theory in the sense of calculating the entropy of the signal that's contained in each of the bounces. So we did this numerically. We did numerical simulation, essentially simulating a hall of mirrors. You calculate the entropy using the standard sort of entropic definition, so the P log P, where P is the probability distribution for the data that you're getting. And without going into too much details of the maths, but what I'm plotting here is on the x-axis, I have the number of reflections in the multipath data. And this U of I is what we call the uncorrelated information. So it's the additional information that I'm getting by having the signal bounce one additional time. And really interestingly, what we see is that actually light that has bounced twice, so not the direct, the signal that has bounced more than once actually contains more information than the direct information. So the information, for example, from the first bounce from the mirror actually seems to contain more information than the direct information that I can get just by looking at Charlie Chaplin. But you can see the significant information across all of the multipath bounces. And to show this is true, this is an example of where I did exactly what we said before, but we're using a radar now. Here I have the ground truth from an optical time of flight camera, but look at the quality of the reconstruction now. This is reconstructed using just this temporal histogram here, where you can actually start to see some of the multipath peaks in this data, but you can see that the reconstruction actually is quite good. And not only could we do this with radar, but we also did it with sonar, with sound waves. Now, the reconstruction here that you see in the middle is a lot more confused and isn't as good quality as with the radar. But I did want to point out this was done during COVID lockdown. And the really surprising thing is that this was done with a laptop computer. So what we were doing is using the speakers from the computer to send out clicks of sound, in a bit like what bats do. And we were using the microphone on the computer to record the return echoes. And this is the data that we're using. So we transformed essentially a laptop into a device that can provide 3D images of the scene in a room. And you can actually see the details of the room. You can see the person moving around. The multipath echoes here are if you look at the temporal histogram, are now really well distinguishable. You can actually see each of these peaks corresponds to a reflection from ceiling, the wall, and then the person, and so on. You can clearly see we've got 1, 2, 3, 4, 5, 6, 7, 8, possibly even 9 different sort of multipath bounces that we're looking at and using to reconstruct this image. Again, just using a computer here, I thought was quite phenomenal. So let me, I don't have too much time left over. I wanted to give you another example of what we're doing, and now really pushing the concept of multipath to the limits. So what I'm going to talk about now is diffuse imaging. So imaging through a very strongly scattering medium. I'm showing examples of clouds here, and you can see that, white clouds, you've got weak diffusion. If the diffusion becomes very, very strong, then the clouds start to turn black. And what is happening here is that the light is bouncing multiple times off not walls anymore, not surfaces, but now off the molecules of the dust, of the particles that form the clouds, and is going around multiple paths. When the diffuser becomes very thick, those multiple paths tend to reflect most of the light, and that's why the clouds are becoming very, very dark in this image. The reason we are interested in what is called diffuse imaging or imaging through complex media is, there are many reasons for wanting to do this. Of course, I just showed you an example of where if you could crack the problem of imaging through a diffusive medium, you would be able to image through clouds or through fog. But what is motivating most of our research is this idea of trying to image through the human body, and in particular through the brain. And there are already even commercial products that you can buy that use what is called functional near-infrared spectroscopy, FNIRS, which essentially relies on using fiber tips to send light in from a source and then detect it from a spatially separated fiber. And essentially, I already mentioned how in very thick diffusive media, very thick cloud or the brain, most of the light actually will go in and then will be back reflected. And so if you send in, for example, 2 different wavelengths, this is why people talk about spectroscopy, you can look at for the differential absorption of blood or the oxygenation of blood, and use that to determine the oxygenation level of blood in the brain. And then you use that oxygenation level as a proxy for brain function and brain activity. This is also, by the way, exactly the same way in which MRI works. These huge magnetic resonance, that's the physical principle by which MRI works. So not using light anymore, but using magnetic resonance. But the point is that this is still built around the idea of trying to detect what is called the BOLD signal. So BOLD is an acronym that stands for blood oxygen level dependent. And so the MRI is also measuring essentially the amount of oxygenation or oxygen in the bloodstream inside the brain. And the dream one day would be to be able to replace these hugely expensive and certainly not portable, not wearable technologies with something which is wearable and gives you the same amount of information. And what would that enable? You know, we already have MRI, we can image the brain. If this were portable and cheap, it would enable something like this. This is data based on data taken from an MRI machine. People are being shown a video clip, and from just looking at the blood oxygenation levels in the brain, this is what, with using some machine learning techniques, this is what the machine believes the person is actually seeing. Okay, so remember, this is only based on blood oxygenation levels from the brain, and the machine essentially is able to read what the person is seeing. It's not perfect, but it's pretty good. And I would argue that what is lacking now is data. And so this is what a wearable device would enable. It would enable this technology to be widely available, usable, and also collect more data and make these reconstruction techniques better. So we're not quite there yet, but I think the future is looking very exciting. So let me show you again sort of a video from our lab where it's an example. So this is a postdoc hand or arm. It's not a brain, but it's just to show you that to prove to you that your body actually is transparent. You think it is opaque, it looks opaque, but especially in the near infrared region, what is really happening is not that light is being absorbed, it is being scattered. It is this multipath effect on light, which is essentially scrambling everything and making you look, making your arm look as if it were opaque. And the challenge here is to now take this scrambled light, multipath light that is transmitted through the body, and somehow find a way to unscramble it. And so in general, you know, what we're doing here is, so you can divide sort of light into different categories depending on how it scatters through the medium. I'm sending here, as sort of like a cartoon, I'm sending in a very short pulse of light. And at the output, what I'm getting is this very broadened, you know, the timescales go here from 100 femtoseconds for the duration of the pulse to tens of nanoseconds at the output. And you can sort of divide light into sort of ballistic or snake photons. These are photons that kind of manage to make their way through the scattering medium without essentially interacting with the medium. These are photons that, if you can collect them, will contain direct image information. But most of the light, especially as you increase the thickness of your scattering medium, will follow these sort of multipath trajectories and will end up essentially providing you no real information. And this is what constitutes the majority of the light that you get out, and is what we call these diffuse photons. So this graph is a bit complicated, but very briefly, we typically quantify the thickness of a material in what we call scattering lengths, or transport mean free path lengths, to be more precise. This is the distance over which the photon loses all information of its initial propagation distance. And this, on the vertical axis, I'm showing the number of photons per second that actually get out of the medium. And you see the ballistic photons, they die away very quickly. After 80 scattering or transport mean free path lengths, essentially all you're getting through is about one photon every age of the universe for a 1 watt laser. Okay, so essentially, I mean, up here you have 1 photon per second. So anything beyond 30 transport mean free path lengths is going to be impossible using so-called ballistic photon imaging. The diffuse photons, on the other hand, are far dominant, even at very thick scattering lengths. These are the ones, this is the region, you know, at 100 scattering lengths and beyond is essentially where you need to be imaging if you want to be able to image all the way through the human body or through the human head. So here's an example of an experiment we did. This is not the brain, this is just an artificial material. It's a polyurethane, which just happens to have the same scattering coefficients and absorption coefficients as the human brain. So although it's a plastic, it's a very good sort of proxy for the human brain. And we have about 5 centimeters of material here, which corresponds to about 80 scattering lengths, so towards the right-hand edge of the graph. And we were just, you can see it's completely opaque, and we're just sort of putting objects in between these two slabs. Here you can see the lens of the camera. This is a mirror sending the light in. So we're just looking in transmission and measuring on the camera. And this is what we see. We have 3 different objects that are hidden inside the slabs. And as you can see, even when I try to do time gating to try and pick out any ballistic photons, and there's nothing to be seen in these images because the light is just so strongly diffused. And then what you can do is you can try and apply to this data, however, an inverse retrieval model. So we're also using machine learning, but in the early days here, we were using a standard inverse retrieval model where essentially you make a guess what your object is, just put in a random pattern, and then you use a forward model to numerically calculate what you expect the output would be, and you compare it to the actual measurement. And you subtract these two, look at the difference with a certain metric, and you try to minimize this, what is called a loss function. Each time going round in a circle, changing the shape of your guess target object until you minimize that difference. So it's like, so if you want, it's an optimization loop. So here's the maths. I'll skip that and I'll show you directly the results. These are the images, the objects that we're actually hiding behind the slabs, and these are the reconstructions. So bear in mind, these images are retrieved from this data on the far left hand here, where you can see essentially absolutely nothing, but through this optimization process, we are using the temporal information here, okay? It's not just we're not only using these time integrated images, but we're using the full 3-dimensional data cube, and this is what is allowing us to retrieve these images. And to prove that the time is actually important, we can change the temporal resolution of our detection. You can see that if you go start at 1 nanosecond, so here I'm trying to resolve a double slit, I see essentially nothing. But as I decrease the temporal resolution down to 55 picoseconds, I finally hit a point where I can really clearly distinguish the two slits. And this is thanks to the temporal resolution, not the spatial resolution of the camera. So temporal information is giving me better spatial resolution information in the image. In the interest of time, I'll skip these slides. But this is really just to say that, again, we've been applying information theory to this problem and trying once again to really try and nail down where is this information actually hiding in the data. And it turns out, so if I look at the entropy for a different scattering, so the same object hidden in different scattering lengths or thicknesses of material, I can see that actually, so I've got temporal axis, just looking at 1 pixel here, I've got temporal axis on horizontal time on that, on the horizontal axis, and the calculated entropy on the vertical axis. And actually the area, you can easily see that the area contained underneath the orange curve, which is the one for the thicker material, actually has more entropy, has more information than the thinner material. Now, so what this is telling us, this is very counterintuitive. It's telling us that the thicker the material becomes, the more the photons are distributed over in time. And this actually provides me more information about the spatial profile of the object, which is kind of what I was showing earlier on. Now, this is very counterintuitive because it sounds like what we're saying is the more diffusion, the more scrambling you have, the more information you have. So, and that's true. That's a true statement based on what we've seen. The trick, though, is the problem, though, is sort of misquoting Shannon's own words. What this entropy analysis tells you is it tells you how much information can be transmitted through your channel, but it does not tell you how to retrieve anything meaningful from that information. So the information is there, but it's highly scrambled. And the more you propagate, the more scrambled it's going to be. And so the challenge now is we've identified that the information actually is getting through this noisy channel in an information theory sense. But now the challenge is to figure out how to continue to extract that information in the form of an image, even over very, very thick scattering distances. So that brings me, just last two slides, that brings me to the end of my talk. And I just wanted to leave you with one last example to give you an overview. So summarizing, I've talking to you about some non-line of sight imaging, how we can use that for LiDAR, multipath imaging, hopefully one day imaging all the way through the body. We're also working on other topics, for example, fluorescence lifetime imaging for biosciences and cancer research. We're also working on quantum imaging and quantum LiDAR. So really do go and have a look at our website where you'll find the publications and the work that we're doing in these areas. One last example, which I'm quite excited about, is recently funded project that we've got to transform our homes into what might be the homes of the future, where the home is essentially constantly monitoring you, but never taking images. This is something which I think everyone is particularly sensitive about. Nobody wants webcams constantly monitoring and taking videos of you 24 hours a day. Rather, it's all about collecting a combination of optical data resolved in time, multipath, radar data, even acoustic data, and using that to monitor not who you are or what you're doing, but monitoring your heartbeat, your blood oxygenation, even mental health, and potentially, the progression of disease and mental sort of neurodegeneration diseases. To give you one example here, we have been working on techniques, and other groups have been doing this as well. But what I think is particularly promising here is that by using these techniques, we can now use a laser pointer, which can be pointed anywhere on your face or on your neck. And it's just simply collected by a camera. This video, I hope you can see it, is just showing an actual recording, real-time recording of what we pick up with the camera. This is just a standard camera, but you can see we're not imaging a person. We're just picking up what looks like a random, what is called a speckle pattern. But by analyzing the flow of these speckles through the image, we can then, and using some wavelet analysis, we can pull out what is called heart sound. So this is not just the heartbeat, it's the actual sound, the vibration of your veins as the heart is pumping. And you can use this heart sound. So here I'm identifying the 4 heart sounds. So typically you only have S1 and S2. That's the sort of so the standard heartbeat that we're all familiar with. But certain pathologies are associated sometimes with S3, but more commonly with S4. And what I'm showing here is an example of a person that was tested in our lab. And this is what we actually detected. And I'm comparing this. The red curve is a digital stethoscope, also placed on the neck, which didn't really see anything. We had the sensitivity to pick up this S4, suggested to the person that maybe, because we were not seeing this in other people, suggested that they go and see the doctor. And actually it turns out that they have actually been referred to a cardiologist because they could potentially indeed have a heart problem. So although this is very anecdotal evidence, it's just to say that these technologies really can make a difference. And actually in our lab already are possibly making a difference. So I'll stop talking here. I've overrun by a few minutes. Apologies for that. But do please contact me if you have any other questions. Look at our website. But I think we have some time now. Ida, so I'll pass the word over to you. I think we've got some time for some questions. I don't actually see, unless I stop sharing. I guess I could stop sharing. So I don't actually see.
Yes. Thank you, Daniele. Thank you, Daniele, for your presentation. I guess I could send you virtual uploads. Daniele, thank you again. And now time is open for the questions. So questions you could give me or directly to Daniele by going to the participants menu and then raise a hand. Or you could ask a question in YouTube channel. So we're waiting for your questions. Okay, I see one question. So I'll give you, Oxorius, you're welcome for the question.
Hi, I was just wondering if this could be applied, if you can use the interferometry to, to further this technique, if you can improve imaging depths in optical coherence tomography, for example, by using the same principles.
You definitely could, I think, yes. I mean, in a sense, the speckle patterns that I was showing you in this very last video, I mean, that is a form of multipath interference, if you want. And this is the fields interfering multiple times with itself, and that's why you then get this random pattern. And that actually is the trick. That's why it is so sensitive, because even tiny, actually nanometer scale, it turns out, vibrations inside below the skin are sufficient to change this pattern, and that's why we're so sensitive we can pick up these signals. But I think you were probably referring to sort of a more active approach to interferometry, where the user has, like on the detector, has an interferometer built into their system. I know there are some groups who are looking into this. For example, so using sort of remote acoustic imaging for the human body. So use a laser pulse to create a small, by heating, to create a weak acoustic signal that propagates through the body. And then that's recorded using a laser interferometer remotely. So you shine another laser and look at how the skin vibrates in reflection. That can be done, and people are looking into this. We personally are sort of steering away from that approach, because it does have some difficulties, because you have to build the interferometer, and the interferometer needs to remain stable. And so if you want a deployable technology, so you want something that, for example, you want to wear, even, think of the brain reading device, for example, or you want something that, you want to hand it over to a clinician, and they just have a little box and they just shine it at someone, press a button, take an image. You can make interferometers robust, but it's a bit harder.
Okay, thank you.
Thank you.
Thank you. More questions, please. Okay, so maybe now I will ask a question. So you're using reflected photons in order to image the objects. So if you will go to the open field or open field setup, how do you organize this reflection, or for the emission of the let's say light, or
So there are multiple answers to this question. So when you're using lasers, the idea is that you're holding the whole device is packaged, so that you've got the laser and the detector together. So for example, I mentioned that some cell phones have this technology in them, and essentially what they have is so this, I'm not sure you can see it, but this little thing here has both the pulsed LED and the detector all on the same identical chip. This is only for monitoring distance, by the way. It's not actually not actually imaging. But normally, you for example, the heart monitoring, the idea is that you have the device and you point it at the person. Likewise with radar, I mean, these radar antennas or transceivers can be tiny, can be this size, where everything is integrated. There are actually people trying to just do passive imaging. So using light sources that are already in the environment, and then finding ways to use those. Or even when it comes to radar, people are even trying to do imaging using GPS signal.
Okay, so maybe I will a little bit improve my question, because if you maybe show the slide with your data from Optica journal, so you presented results, but I don't understand the setup of the experiment. So objects were over the corner, or?
No, so in that work, that was direct line of sight. So that really, that work, okay. So that multipath, yes, sorry for the confusion there. So the first part was non-line of sight. I mean, we have done also the optical work for non-line of sight. It's very generic, really.
Okay.
But what I was showing there, those videos like the yellow people moving on the blue backgrounds. So those videos were just direct line of sight. There's a person
thank you.
You just flood illuminate. So you need to illuminate the whole scene, and then you just collect everything that comes back. But you're collecting this, you'd never have a camera. You only have, just think like a photodiode, for example. That's all you have. Or radar, radar, you don't have radar cameras. I mean, radar just picks up a blip that comes back, and so you're just collecting the echoes.
Okay, so thank you. Now, Vytautas Jukna has a question, so please, Vytautas.
Oh, hello, nice to hear you again and see you.
Hi,
I have a question again, which is related to riders. So I was thinking about how to be invisible in the sense with your, how to not to be able to be seen with your camera. So maybe the turbulence with some dust particles should affect it very much.
So no, that's not the way, because, well, it could be in some cases, but where part of the reason for going down these routes is precisely to avoid problems like this. So to always be visible. So I guess one could also ask the question, well, why, we've got cameras where we have got them on my phone. I don't need a radar that can do imaging, but actually you do. So the point of trying to do radar imaging or ultrasound imaging is because cameras stop working when there's fog, when there's dust, when there's smoke, a house on fire or something. Our vision and cameras can't help us anymore. But radar and ultrasound, sonar, keep on working. And actually all of our cars, all modern cars now, already have radar and sonar on them. So you have ultrasound for parking sensing, not imaging, but just sensing for parking, assisting you in your parking. And you have radar also as proximity sensors for looking in other directions for other cars approaching, for example. These could all be transformed into imaging devices that work all the time, even when otherwise it would normally be impossible. Things would be invisible because of smoke, fog, or dust, or whatever. In order to become invisible, you're going to have to play some clever tricks. So, for example, looking around corners, the non-line of sight stuff, we discovered that the only way to become invisible there is if essentially you have to really stay right up against, attached to the wall. Then you become invisible because essentially the scattered light can't really reach you. So if you find a way to make sure that you can't be reached by the scattered light, then, and you understand the minimum of the physics of how light is scattered off a wall, then you can look for blind spots. But with the radar, that becomes actually extremely hard because, light has this property, it decays very quickly. So if I don't detect you within a direct, 1 or 2 bounces, then you're safe, you become invisible. But we saw with radar and sonar, I can detect up to, 10 bounces in a room. So you really have to, it's going to be very hard to be completely invisible.
Okay, understood. Not to bounce anymore. Okay, thanks.
Exactly, yes.
Thank you. So I don't see any raised hands, so maybe, and we already passed time, so maybe I would like to thank you again and my virtual applause to you again. And I guess that this session already is finished. So thank you again for the audience, for the students and scientists for the attention.
And yeah,
very
thank
much.
you everyone. Thank you so much for the kind invitation, the opportunity to talk to you.
Thank you, Daniele, very much. Thank you again.
Nice to see friends.
Okay, see you.
Bye, Magirkas. Bye, everyone. Thanks.
Okay,
Bye.
so see you, Daniele.